I'm John Tyler, and I'm going to show you why we continue to have problems with draining groundwater. We'll also discuss how to design and build effective drainage that can easily accommodate all demanding applications without ever requiring replacement. So let's begin. Where does groundwater come from? All groundwater comes from rain. Rain is a part of the water cycle, which is a never-ending circle that guarantees a function of life. Each part of that water cycle is governed by rules set by nature that have been operating ever since the beginning of Earth. Since the source of rain is from evaporation from the bodies of water and transpiration from the earth, the water is returned by rivers and migration through the earth. So how does water move through the earth? A large part of the rain is returned to the oceans and lakes through surface runoff. Surface runoff travels by flow, which can be very fast or slow. Rapid flow is what's responsible for the erosion visible along riverbanks and streams as it's dislodging and carrying debris and soil particles. The water will appear dirty. When the flow is reduced or stopped, those particles will settle to the bottom. After floodwaters recede, there's always a layer of mud covering that previously flooded area. Part of that rainfall soaks into the ground and migrates downward to the water table. This migration is aided by plant roots and propelled by gravity and pressure. Water in the ground does not travel by flow, since there are no open spaces. It does travel by capillary through the pore space. Pore space is the area between the soil particles. Capillary is a process where water can travel through the pore space by coating the surface of the soil particles, and since water molecules attract, more water is then pulled into mass without displacing the soil particles. This is a big difference and very important. When water travels by capillary, it can move through the earth without disturbing the soil. This is a significant factor in the effective drainage of groundwater without causing a blockage. The two most important points to remember are: 1, water on the surface of the ground travels by flow. Flow is simply gravity as the water moves to the lowest point in the area. 2, water below the surface of the ground travels by capillary through the pore spaces without disturbing the soil particles. Now, let's get to talking about draining soil. The standard assembly of draining soil uses a large diameter pipe with rows of slots cut through that pipe. The pipe's installed in a trench 30 centimeters or 1 foot wide with a 5 centimeter or 2-inch layer of drain rock below the pipe, followed by the pipe placed in the center of that trench and then filled with drain rock to a height of about 30 centimeters or 1 foot. Backfill material is then placed over top of the assembly. We constructed this assembly housed inside an acrylic box so that we could test and visually see its performance. We used sand for the backfill material, and since the spaces between the drain rock aggregate are large, a good deal of that sand migrated to the spaces before we could even start the test. The bottom of the container has holes drilled so water can exit the system and is visible when it's through the assembly. We can follow the water down through the sand. As it moves through the sand, it's traveling by capillary, so no movement of the sand particles can be observed. Movement through the drain rock layer is more rapid since the spaces between the rock aggregate are so large. At this point, movement of the water changes from capillary to flow since there are large open spaces for it to flow. This is also washing particles of sand to the bottom of the container where they will begin to build up. Water is now visible coming out of the bottom of the container. As more water appears out the bottom, a quick check inside the pipe shows virtually no water. With a substantial amount of water now exiting the box, another check inside the pipe confirms the fact that almost no water has entered the pipe. Even a hand placed inside the pipe comes out dry. This is startling, considering this is the accepted standard system for draining groundwater. When in fact, this system cannot work in the same way we expect it, because there is no pressure. It is the same as adding water to a glass full of ice cubes. The water is going to flow through the spaces and go directly to the bottom. There is no pressure in the system, only gravity causing the water to fall. The behavior of this system demonstrates another very important point to remember. Water cannot be collected in a gravity drainage system as it migrates down. There must be pressure from the buildup of water to force the water into the collection assembly. The industry name for this pressure is head. Phrased differently, while the source for groundwater is rainfall from above, from a drainage collection point of view, the source is always a rising water table from below. Drainage must always be oriented to intercept the rising water table. Now on to the problem of blocked pipes and filters. The system began by simply drilling holes in the pipe. Later, ribbed, thin-walled, large diameter pipe with factory-cut slots became the standard. The migration of soil particles inside the pipe remained. Later modifications to the system included encasing the pipe in aggregate, hence the name drain rock, and pipe wrapped with geotextile filter. Well, encasing the pipe in drain rock changes the drainage assembly considerably. It creates a reservoir into which soil particles can settle and may delay the buildup in the pipe, but it also creates a flow channel for water. As shown earlier, the water will flow to the lowest point, which is the bottom of the drain rock, and it will simply flow through the drain rock without going into the pipe. The flow will also wash soil particles down into the large spaces between the rock aggregate, completely blocking it in a short time. Plant roots growing through the slots are also a common blockage problem. Filters are the most recent modification to the perforated pipe drainage system. It's an attempt to block the soil particles before they can travel into the pipe. Filters used for this purpose are geotextile fabric wrapped around the pipe. Filters are just fibers with spaces between them. As the water migrates through the filter, fine particles will be trapped in the spaces between the filaments. Eventually, those trapped particles accumulate and block the filter. This photo shows the drainage assembly from an actual job site. An inspection of the pipe confirms it is in good condition with the slots clear. The cause of the failure is the filter wrapping the pipe completely is blocked by fine particles. Filters work when they're new, but from the moment they're put in service, they deteriorate in efficiency as they block particles until they become completely blocked. While a filter to clean the air in your car can be changed easily when it becomes blocked, it's not possible to change a filter using a drainage system without a complete excavation and replacement. Changing the system at frequent intervals makes this the most expensive system on the market. Now, nature has provided a mechanism for water to migrate through the soil by capillary without transporting or disturbing the soil particles. Capillary moves in all directions equally, including up. Capillary is responsible for the ability of paper towels and all tissues to wipe up spills. We use it every day. Watch what happens when we touch the surface of the water with a corner of the paper towel. The water moves into the towel quickly and straight up. When we wipe the spill, the water is held in the spaces between the fibers of the towel by capillary. The same way the soil holds the water which plants need to survive. Now let's place the bottom of a paper towel into wet soil. Again, the water moves vertically into the towel, and a closer look shows soil particles are not carried into the towel along with the water. The water is clean. Capillary is the basis for a new generation of drainage products introduced approximately 23 years ago. While they were revolutionary at the time, they've proven to be effective in a wide range of drainage applications in many countries around the world. Today, both Waterbelt and Soil Spaghetti used capillary for water collection, collecting water directly from the soil without the need to use drain rock or filters. Waterbelt is a thin belt with micro channels embedded across the width. The micro channels are accessed by continuous slots running the entire length of the belt, and water entering through the slots is held in the micro channels by capillary. Once water fills the micro channels, it flows through the channels to be discharged. As the water is discharged, a siphoning action also pulls additional water into the channels. In most installations, Waterbelt is installed with the slots facing down for two primary reasons. The first reason was demonstrated earlier, where saturation of the pore space generally starts from a buildup of water below, the same as filling a glass of water. The underside of the belt is perfectly positioned to intercept the rising water. The second reason is the most important and the key to the success of our system. The water must migrate up to fill the microchannels. Soil particles can't travel up. In fact, when soil settles, there is always a reduction in height. Additionally, water migrating by capillary does not transport soil particles. As a result, only clean water is collected in the microchannels. It is a natural filter system from nature with a track record of 1 billion years. The discharged water is very clean and eliminates the need for a drain rock settling area or the need to use additional filters. Without any physical disruption, the system will operate perfectly without clogging, without maintenance, and without the need for replacement caused by blocked pipes. Generally speaking, most drainage system problems originate from using components which were not designed for the purpose. Pipes were designed to transport water and do a perfect job for this function. They were not designed to collect water and as a result do a less than adequate job when tasked with this function. Although the discharge rate for a pipe this size is approximately a 5-gallon pail per second, it has no bearing on the drainage capacity since the flow is limited by the amount of water it can collect. Only 2 to 3% of the surface area of the pipe has slots for water to enter. For a 4-inch pipe, it is equivalent to 15 square inches for 1 meter of pipe. Compare that to Waterbelt, where the entire underside is covered with collection slots representing over 60 square inches for water to enter, and it is obvious the belt will collect much more water and much more quickly. This is also the reason drainage pipes are large. They need an expanded surface area for collection. When water rises to the level of the belt, water level A, 100% of the belt, 63 square inches per meter, is available for collecting water. Perforated pipe with water at the same level can only offer 3.75 square inches per meter for collecting water. Even if the water rises halfway up the pipe, only 7.5 square inches are available for collecting water. Designing a drainage system using components which were never designed for a particular task will result in a problematic compromise where additional components must be added to reduce the shortcomings of the system, such as adding drain rock or filters. Waterbelt's a very efficient mechanism for water collection, but it's impractical to claim that it will transport water as efficiently as pipe. The capacity of the microchannels is simply too small. The solution is combining components based on their strengths. In other words, the combination of Waterbelt, a perfect mechanism of water collection, plus pipe, a perfect mechanism for water transport, eliminates hundreds of years of failed drainage problems caused by blocked pipes. A Waterbelt drainage system can be designed to accommodate all demanding applications by adding strips of belt or increasing the length of the belts depending on the soil and water conditions. Now, notice how clean the water discharge is? There are 3 main assembly configurations designed to suit different application requirements. The most common assembly is the horizontal configuration. With this assembly, belts are installed into a collection pipe with the spacing and lengths of the belt chosen for the type of soil and the severity of the water conditions. This assembly is ideal for sports fields. A water drainage system can be designed so that play can be resumed as soon as the rain stops. If you are serious about drainage, Waterbelt is the correct solution. The drainage system discharges into catch basins. This field has 6 catch basins, of which this is only 1. This is an impressive display of drainage capability. landscaping, parks, and all green areas, golf facilities, high water tables under slab installations, infrastructure, road beds, rail beds, airports. A large-scale test for an agricultural application was carried out by a large plastic pipe manufacturing company. While they are a direct competitor, they shared the test layout and data with us. It involved a 2-acre site with half the area installed with perforated pipe and the other half installed with Waterbelt. After installation, the area was watered intensely. The results are astonishing. The pipe solution stopped working at the end of the first day, while Waterbelt continued to work for 2 more days until there was no water left to collect. Additionally, Waterbelt collected an average of 3 times more water during an equal period of time. Water harvesting. It's becoming increasingly important as pressure on water resources grows. In a remote mountainous region, above-ground dams built to store and supply water for small villages have been silted over and dried up. A novel solution was developed to collect water from seepage in what appeared to be a dried riverbed. Waterbelt was installed in parallel channels dug into the riverbed where there was evidence of water. The collected water was channeled into a central reservoir for distribution to the homes. The results were impressive. Yields were in excess of expectation. The water was clean, even surpassing the national drinking standard, and capital costs were 40% less than other solutions. There is no equipment and there is no maintenance required. Based on this success, we've done over 30 installations completed for this owner. Another popular installation method is the vertical assembly. Belts are installed vertically, leading into a pipe running horizontally along the footings. This is an ideal installation for behind retaining walls, or placed around the outside of buildings to prevent hydrostatic buildup against the walls. Any water buildup against the wall is immediately collected by the belts and transferred to the pipe below and discharged. Testing in both sandy soil and clay shows Waterbelt starts to work as soon as water comes in contact with the surface of the wall. In both cases, there's no water discharge from the pipe solution until the water reached the bottom of the container and the buildup of pressure was enough to force the water out. The Waterbelt solution produced a discharge as soon as the pore space saturation in an area reached 100%. Even though the water penetration in the profile was at an early stage. Waterbelt is the only effective solution to address the buildup of hydrostatic pressure. A Waterbelt assembly installed vertically can collect seepage through earth dams and help prevent saturation of the soil in areas surrounding the dam. A special Waterbelt assembly offers a simple and cost-effective solution for slope rehabilitation and retaining wall repair when excavation is not practical. Sections of shaped PVC pipe are wrapped with Waterbelt so the sections can be added together to form a water extraction assembly of any length. Water is collected over the entire pipe surface, flows to the transfer joint through the microchannels where it is transferred to the inside of the pipe for removal. The water is transferred at each joint so the evacuation function can't disturb the collection function. Installation is as easy as drilling a hole into the correct length and inserting the entire assembly. Waterbelt horizontal drain is a cost-effective solution to difficult slope stabilization and retaining wall challenges. Soil spaghetti. Let's talk about soil spaghetti, the most recent technological innovation for draining groundwater. Soil spaghetti also collects water directly from the soil by capillary and has all of the advantages enjoyed by Waterbelt. The differences are in the mechanism for collection and the preparation and installation methods. While Waterbelt collects water into a small internal cavity, soil spaghetti uses specially shaped rods which then combine together, create an expandable network of channels which collect and transport water. Water held between two rods demonstrates the properties of water, surface tension and capillary, which enables the collection and suspension of water in a network without draining out. It also demonstrates the genius of nature where water, held in the soil with less than 100% saturation, can't be drained by gravity drainage systems, as this is the water plants require for healthy growth. In other words, Waterbelt and Soil Spaghetti will drain all the excess water from the soil, but can't drain the water required for plant growth. The installation of Soil Spaghetti is very simple. Make a trench, place the spaghetti along the bottom of the trench, cover the top with geotextile or solid plastic material, and then backfill the trench. The cover over the spaghetti is not required as a filter. It is required to prevent soil particles from falling into and blocking the network created by the rods. The underside is left open in full contact with soil for collection by capillary. This free-form configuration is suitable for a wide variety of applications, offering an inexpensive solution for isolated wet spots to repair for sports fields without removing existing turf. The physical properties of Soil Spaghetti are impressive. The rods are manufactured from a semi-rigid PVC, which, in addition to an extremely long service life, the network is supported throughout its shape and can withstand all expected factors which would crush drainage pipe. Even tree roots are not a significant problem since Soil Spaghetti and the water can simply go around them. A trench with a width suitable for the amount of spaghetti to be installed is the only requirement. A depth where the embedment of the spaghetti is a minimum of 20 centimeters is recommended so the spaghetti is not affected by any surface activity. Since the Soil Spaghetti network can be greatly expanded over the limitations of an internal cavity, Soil Spaghetti has the ability to transport water over considerable differences. While it is compatible with pipe networks and can be discharged into a pipe network, many applications can be completed without the need for additional pipe. Soil Spaghetti is available in specific shapes for compatibility with different applications. The most common spaghetti pipe is manufactured in a round shape, and the diameter is compatible with a 2-inch pipe fitting so that it can simply be connected to a pipe network. It is the only pipe drainage product which can collect water without having soil particles enter the drainage system. It can be a standalone drainage solution, or it can be cut to any length required for an effective solution. Spaghetti pipe is a practical repair method for existing retaining wall drainage, as well as a fast and easy solution for slope stabilization applications. It functions similarly to Waterbelt, horizontal drain, but the collected water must discharge along the full length of the pipe, and is not as rigid as horizontal drain during installation. Spaghetti pipe is recommended where the required length of the pipe is less than 5 meters. A segmented board configuration is ideal when a high capacity, high compressive strength coupled with the ability to transport the collected water without pipe is required. Typical applications include road beds, railway beds, where there's a pumping as the train cars pass, airports, and complex civil engineering projects. Water is universal. It does not know or recognize borders between countries. The behavior is the same everywhere. Are Waterbelt and Soil Spaghetti revolutionary products? Yes and no. The products are unique, but they're simply harnessing what nature has been using for billions of years in plain sight. And they are very successful. There are many existing and future possibilities for economical and effective water management. We have only concentrated on some basic drainage methods, problems we face every day. There are existing and new opportunities in different fields. Possibilities may be as a primary filter for water collection and desalination operations, as a primary filter using river water for bottled water operations, rainwater harvesting, collecting water from fog, and many other opportunities. One of the most obvious applications is where the loss of water to evaporation can account for a 90% loss in utilization. This is in sprayed irrigation. With the increasing scarcity of water resources, a method of below-surface irrigation would result in considerable savings and preservation of a shrinking supply. Our system waters plant roots directly underground and eliminates water loss due to evaporating. There is up to 90% reduction in water consumption. The supply lines can be permanent below ground or temporary above ground and retractable. Our system is gravity fed by reservoir height. That means no mechanical equipment is required. That means there's no maintenance. The system is environmentally friendly and sustainable. Our system has an extremely long lifespan. I hope you've enjoyed the presentation. We are always ready to assist you with any drainage problems you have. We would also be pleased to discuss any area of cooperation for additional applications or the development of existing concepts for Waterbelt or soil spaghetti.